Now we're going to talk about the useful consequences of independence, which is that it lets us factorize things and move a little bit beyond the thinking population data set and thinking about densities and how that helps us. So first thing is that if we're writing out the joint distribution of two variables x and y, if we know that x and y are independent, then that lets us factor this joint distribution in a slightly nicer way. So we know this top line equation is, we covered this last time. We can always factor a joint distribution into the product of a conditional and a marginal. And that's because the definition of the conditional is just the ratio of this of the joint to the marginal. So this is the multiplication rule. I've just moved this thing over to the other side. So this is always true. Now here we've just used the definition of independence to say if they're independent, then this conditional probability is the same as this marginal probability. Knowing y doesn't tell me anything about x. So this is the same as the marginal probability. So what this says is that the joint probability of two independent variables is just equal to the product of their marginal probabilities. And knowing this, we can also show something that should kind of be clear already that we've been kind of skirting around, which is that independence is bidirectional. If y is independent of x, x is independent of y. It's not like one is independent of the other. They're both mutually independent. And this is easy to show with this factorization, because if we take the joint distribution, we can factorize it this way, y given x times x. We can also factorize it the other way, right? X given y times y. And then here we can show, because of independence, that this conditional distribution is just the marginal of y. And we can cancel those, on both sides, the y and the y. And we're left with just this conditional probability distribution of x given y is equal to the marginal of x. So by starting out by assuming that y is independent of x, we've shown that x is independent of y. And so those two things they mean the same thing. So there's no, it's bidirectional. Independence is mutual, which which makes sense. We've seen it in all our examples. So in terms of density functions, we have the same thing. We have the same a relationship. If x and y are independent, that is the same as saying that the conditional density of x given y is equal to the marginal density of x. And similarly, we can factor not just the probabilities, but the densities themselves. Again, this is obvious if you think of densities in the discrete case as just being equal to the probabilities, like these are probability mass functions. Then this is very clear. And here, what we're showing is that the relationship between some particular joint distribution and a marginal distribution and a conditional distribution. So remember that the conditional distribution is what we get when we take a slice here. So we're conditioning on y equals some particular column value of y. And we're taking that distribution, and then we have to scale it so that all of those, basically so that the denominator is 1 again, right? Or that they add up, these probabilities all need to add up to 1. And the number that we need to scale that by is precisely the sum of all of these probabilities. So I take those over. So for example, 0.07 divided by the sum of all of these numbers is 0.1, okay? And now the marginal probability we know is in this case, the sums across the rows of each of these. So here we're ignoring what the value of y is, and we're just saying what is the probability of x. And so we're summing 0.03 and 0.07, and here we're summing 0.06 and 0.14. So this is a quick review of what we did last time. I'm just showing you an example of a case where the marginal and the conditional end up being the same. And when this happens precisely when the columns are multiples of each other. So for example, here it's easier to see actually with the rows. So here we have 0.03 and 0.07. So if I take these numbers and I multiply them by 2, I get these numbers. If I take these numbers and I multiply them by 2, I get these numbers. If I take this and I multiply it by 3, I get these two numbers here. So you can see the rows are actually just constant multiples of each other. And actually, it's the same thing with the columns. It's just that it's not a round number, but basically this column here is the ratio between them is 3 to 7. So same thing here. This ratio is 6 to 0.14, and that is if you just divide by 2, that's 3 to 7, 3 to 7, 3 to 7. So when these columns and rows are multiples of each other, you always get this situation here where if I take the conditional and I scale it up, right? It's essentially like the same pattern. If you think of it that way too, like if you look at the color pattern, right? So here I have like light, darker, darkest, light, right? Light, darker, darkest, light. If I just take one slice of that versus I mash it together, I'm going to get the same pattern. Again, that's hand wavy. I'm just trying to give you intuition for what's going on. This is similar to the kind of intuition I was trying to give earlier, where you're dividing up the people into a grid, and you're saying, is the grid line kind of jagged, or is it at a right angle? Mathematically, you can prove that these two columns are going to be multiples of each other, that these rows are all just going to be multiples of each other. Hopefully that helps. Another way to see that, so this is in a discrete case. In the continuous case where the joint, so here we have the kind of heat map of the joint density. In the continuous case, we can kind of look at this as a 3D plot like this. And so here we have X and Y, and then the height of this indicates kind of how many people, how crowded it is at that point in XY space. And what we're saying here is that these two columns are scalar multiples of each other. So they have the same pattern of light to dark. And the equivalent here, if you think of the low values as light and the high values as dark, we're saying that, so there's not columns, but there's different slices, right? There's not columns and rows, but you can think of different slices either in the X plane or along the X axis or the Y axis. And these slices should have the same pattern of light to dark. And in this case, that means that the kind of up and down pattern of them should be the same. Should be scalar multiples of each other. So if I look kind of from this direction, I'm sitting over here where this X is, and I'm looking at this curve. And over here I'm plotting the red curve, and I can plot the pink curve. It's going to be I don't know if I have it shown here. No, but the pink curve originally will be lower, right? But what I'm showing here is that if there is some number that I can multiply this pink curve by, and it'll line up exactly with the red curve. I just need to scale it up by some constant. So this times 2 or something like that will equal to the red curve. So when X and Y are independent, you can always do that. All right. So based on that information and understanding, let's say I have a joint density between X and Y. It doesn't really matter which is which, but let's say we have X up here and Y over here. And the question is, can we fill in these missing values such that we have independence? So easy way to recognize this. I mean, there's multiple ways we can do it, but let's just say we know that this column here has to be a scalar multiple of this column here. What is that scalar multiple? Well, let's look at the ratio here. So this is 2 to 3. So for every 2 units of probability on the left, I need to have 3 units of probability on the right. So if this is a 0.8, then over here I need to have a 0.12. So all I've done is, so if this is 0.2 units, then this has to be 2 of something, so it's 0.04, and then 3 times that is 0.12. Similar here, if 18 is, again, if you want to be very like brute force about it, I'm solving this problem, right? Where I'm just saying 18 is to 3 as something is to 2. Similarly here, I was like, 8, 0.08, or like 8 is to 20 as 12 is to 30. Okay. And yeah, strictly speaking, it's like this, but whatever. It doesn't matter. I can divide by 10. And so you just solve for x here. You should remember how to do this. 3x equal 2 times 18, or divide by 3 here. 2 times 6, right? Okay. So actually, both of these are 0.12. That's all you have to do. Okay, so I said that if 2 variables are independent, then basically these 2 columns need to be scalar multiples of each other. So it's kind of like saying y equals little y, whatever that is, has to be the same as the probability that x equals 1, given y equals little y, times some constant. And I don't care what the value of y is. This constant is always the same. It doesn't depend on what that value of y is. That's saying that these 2 values, I can get this one by multiplying the thing on the left by the same number, c. So times c times c times c. Okay. So why should that be the case? Well, if they are independent, then this factorizes, right? And here I have a c. And of course we can cancel these 2 things are the same number. And so what we have is that this, right? The ratio of the marginal probabilities is some constant number that doesn't depend on y, which is the case, like, right? So let's say that the marginal probability of x is 1/2. Then this is 1/2, this is 1/2, and then our magic number c is just 1. If this number up top is 1/3, then this is 2/3. It's 1 minus that, and then our magic number over here is 1/2. So basically, no matter what, right? If these 2 things are independent, then there is some constant c that I'm just always just multiplying one column times that number to get the value in the other column. So this proves what's there on the previous slides, in case that wasn't clear, which probably wasn't. Okay, so another problem. This one's a little more complicated because dealing with densities and formulas, so you may be a little less comfortable notationally, but I'm just trying to give kind of an avenue, a look into this sort of thing. So let's say I have this joint density, and the question is, are x and y independent? It may not be obvious to you, but in fact they are. And the reason is because this part right here is in fact a density function that only depends on x. And this thing here is a density function that only depends on y. And you may recognize these as in fact the density of a random variable, a uniform random variable on the interval 0, 0, and 1. And this is the same. But this one is depending on x and this one is depending on little y. And so this tells you basically that x has, because it can factor, then this implication goes both ways, right? So it's not that if x is independent of y, then we get this factorization. That is the case, but it's not just that. It's also that if you can factor it, then it also goes it goes the other way. Then you know that they're independent. So saying that these things factorize is the same thing as saying that the two random variables are independent. So just by the fact that I can see that I can write this joint density as a product of two densities, one of which only depends on x, one is only depending on y, means that these two random variables are independent. And in fact, if you were to plot this, make a 3D plot of this in R, which you could, in fact, I mean, that's a good exercise. Just go to, if it's not obvious how to do it immediately, go to ChatGPT and say, okay, if x is uniform on 0, 1, and y is uniform on 0, 1, make me a 3D plot using R of the joint density. Try that out. Or maybe even type this in, right? So say my joint density is the indicator of 0, 1 of x times the indicator on 0, 1 of y. Make me a 3D plot of that. So what you're going to see is this. So here's x, and here's y, and this is the density, the joint density of x, y. And you will see that, let's say this is 0, 1, 1. The plot that you get will look like this. That's terrible. Plot that you get will look like this. Okay. So this function takes values 0 everywhere over here, and basically everywhere outside of this box, it's 0. Another way to visualize this might be as a heat map on the xy plane. So here's x and y, and then here is 1, 1. So here we have an area of high density, and elsewhere it's all 0. That is the joint density. So why does this kind of picture make sense, or what's special about this in terms of the independence? Well, I told you that if you slice this along a particular axis in x or y, let's do the screen, right? So let's say I slice it here along this line. What's the picture that I get if I'm standing and I'm looking in this direction? In other words, what is the conditional, let's say this is the value x star, what's the conditional distribution of y given that x equals x star? It's going to look like this, 0, and then, because I'm just slicing it, right? So what does that slice look like? It's going to look like that. What about if I sliced at a different point? What if I sliced over here? Well, it's going to look the same. So no matter where I slice an x, I get the same shape for the conditional distribution of y. And vice versa, if I'm slicing in y, I'm going to get the same shape for the conditional distribution of x given y. And in this case, it's not even scaled. In this case, it's literally the same thing. But that doesn't matter for independence. We just need them to be the same shape, the same thing scaled up or scaled down. All right. So yes, they are definitely independent here.